Okay, hello everyone. Welcome to another one of our Landscapes Live seminars. For those of you who haven't come to one of these before, just wanted to go over a few things before we get to today's talk. So as a reminder, please could everybody keep off their microphones so that we don't interrupt Victoria's talk. Um, 5 minutes or so before Victoria finishes, we will open the chat and we'd encourage you to post any of your questions. If you would like to ask a question yourself rather than writing it down, if you just want to raise your hand and we'll get to you. Just as a something to note, we are recording this particular talk at Victoria's permission, and we do upload all of our talks to our YouTube channel. And so if, please definitely go and have a look at the back catalogue. We've got lots of different people that have given talks over the years. And so, yeah, with that, I want to thank you, Victoria, for agreeing to do a talk for us today. And we're really looking forward to hearing about the work that you've been doing over the last few years. Okay, Victoria, the floor is yours.
Thanks. Hopefully everyone can hear me. So I will be talking to you today about my work that I've been developing at the GFZ over the last couple of years and my postdoc here as part of the Gyroscope project. So in collaboration with lots of my co-authors, so Taylor Schildkin and Andy Heller, Fergus Leonard, and Andy Wickert as well. So without further ado, so one of the big sort of motivations for this study has been looking at the climate records in the Quaternary. We observe that climate has shown these sort of incredible change in cyclicity and variation, starting at around 1 million years ago, which is in the mid-Pleistocene, so the mid-Pleistocene transition, where the climate has changed from these 41,000 year orbitally forced sort of cycles into 100,000 year cyclicity, which is known to sort of affect global climate quite intensely. One of the ways that it's then reflected on landscapes is that, for example, in the European Alps, as sort of seen here in Pierre Val's work, there is evidence of accelerated geomorphic activity in response to probably this increased climatic forcing. So starting 1 million years ago, they've observed in thermochronology data this increased exhumation. As well as we observe landforms sort of showing 100,000 year cyclicity. So this periodicity that is associated with the new stage of climate forcing after the mid-Pleistocene transition. So one of the places that we think, okay, can we actually observe these kind of changes? We need to be able to see lots of climate forced geomorphic activity. So a place that we think we can actually see this and observe this kind of phenomenon is in southern Patagonia. So I'm going to now talk you through why I think this is a fantastic landscape for studying general climate cyclicity. So specifically, I'll be looking at southern Patagonia, about 50 degrees south, at these two river systems that actually form one, so the Rio Santa Cruz and the Rio Chojén. So they are fed by glacial meltwater from the southern Patagonian ice field over here in the west that drains into the proglacial lakes of Lago Argentino, Lago Viedma, and then drain and flow freely all the way into the Atlantic. So these are these river systems here. And they're about 270 kilometers long, so they really span the entire Patagonian foreland. Tectonically, this region, although it is part of the Andean subduction, a lot of the crustal or very active crustal tectonics, especially at around 50 degrees south, has been ceased by the Miocene, so by the late Miocene. So this region is actually very sort of crustal tectonically speaking, very inactive. However, there's a lot of geodynamic action related to the subduction of the Chilean triple junction and formation of this asthenospheric slab window that has been migrating northwards for the past 12 years. So again, sort of just talking about crustal tectonics, there's a lot of Andean tectonics, so there are lots of crustal shortening that has happened in the Andes, but the rivers that we're looking at are all east of the thrust front. So we know that any landforms or terraces that might form on these rivers are going to be undeformed tectonically. Again, sort of geodynamically, we have this very active region with lots of very young basaltic magmatism that has a very strong mid-ocean ridge geochemical signal. You have very, very high heat flow. So the region is very, very hot. The asthenosphere is very hot. And it's a region where we also observe shear wave, very low velocity shear wave anomalies. Yes. Again, it's also a region where there is the lithosphere is very thin, so it's about 30 kilometers thick, which is not much thinner than the actual crustal thickness. So we have a very, very thin lithosphere. Again, just highlighting the existence of this low velocity anomaly, which has been associated with high asthenospheric temperatures. In terms of climate, the growth of the Andes has generated a rain shadow that stops at about the Andean front. So where you have a very wet climate in the western part of the Patagonian Andes, but an incredibly dry climate in the Patagonian foreland since the Miocene, which is very conducive for the preservation of landforms along these rivers. We have also a very long and really good records of glaciations. So either that being preserved in, for example, till records between dated basalt flows. So this is a very classic example from the region, the Cerro del Fraile, where there's been lots of glaciations dated to as recently as the last 1 million years. So the Quaternary glaciations are very well dated, as well as a very good record of glaciations through dated moraines. So this is some very recent work by Mati Romero, dating some of the moraines coming just east of Lago Argentino. If we look even further out from just our region, the Patagonian record of glaciations is very dense and very continuous in places. So these are, here I'm showing a map of all the locations where we actually find evidence for glaciations, whether them being maximum or minimum constraints on ages, so basalts flowing atop or below glacial deposits, or whether they're moraine or glacial outwash terraces that have been dated with cosmogenic nuclides. So we have a very strong sense of the timings of glaciations and a very good record of it in this region. And finally, we think about this ice extent, these glaciations, the very large glaciations. These rivers have not actually been significantly affected by ice. So a lot of the fluvial geomorphology here is also presented despite the very extensive glaciations in the region. So if we zoom in into this river, we can actually start seeing some of this beautiful geomorphic record that I'm trying to look at in the river. So the astute and well-trained eye will identify some of these fluvial terraces down here along the bank of the Santa Cruz River. Ooh. And when you go there, you sort of see these very spectacularly preserved terraces. So these are very, very large landforms, very, very flat surfaces that without much vegetation owing to the lack of rain, but very windy. This is also, when we do get exposure to the terraces, this is what they look like. So they're very classic fluvial terrace succession that you observe with lots of imbricated cobbles and pebbles. And that these terrace risers are actually really large. So they're, over 20 meters in some cases, but they are very prominent landscape features. They're not small cut and fill terraces. So we are here in a very tectonically, so crustally speaking, quiescent region that is climatically influenced by ice. So ice and climate must be exerting a very strong control due to the glaciations, and also very geodynamically active region landscape. So what can these terraces tell us about the role of climate and mantle dynamics in shaping this landscape? And can we use this record to find something out about whether it's actually recording the mid-Pleistocene transition, and how might we use these records to investigate that? So again, just sort of showing you the topography. This is a DEM of the region. So you can actually see perhaps a bit better here, these really beautiful fluvial terraces that are preserved along the entire length of these two river systems. So the first thing that we did is identify some of these regional basalt flows. And the reason why they're important is because they form a really good geomorphic marker. So they erupted between starting around 3 million years ago, and they infilled the Paleo Valley of the Santa Cruz River as well as the Shohen River, the two rivers I'll be talking about. Santa Cruz is the one here to the south, so the Shohen is the one to the north. If we zoom into this very specific location here, which is quite a key location, the Condor Cliffs, this is what it looks like. We have these basalts that infilled the Paleo Valley. The present-day river is down there. Across the river, we see again, so this is the lowest terrace of the sequence. This is the highest terrace just above the basalt, and the basalt is here in this very prominent cliff. Luckily, so the difference in elevation here is about 180 meters, and luckily, someone has dated the top of the basalt flow with potassium argon ages, and it's dated to about 1.7 million years ago. So that sets us a really nice regional stratigraphic age constraint for the ages of our terraces and the timing. So everything from the sort of T6, so this kind of higher terrace, up until the younger terraces must be younger than 1.7 million years. That also gives us a long-term incision rate of about 105 meters per million years. So the next thing, following the basalts, we identified some of the moraines. So we can really identify what is a terrace that hasn't been modified by glaciers, so we're only looking at the fluvial part. And the really big importance is that these moraines are also associated with some of the outwash terraces. The moraines are oldest to the east and the young towards the west. So the glaciations have become smaller over time. And a lot of them are, the moraines themselves are associated with terraces. So for example, this is a nice example again from the same location, Condor Cliffs. We see this moraine here, the big boulder at the top of the moraine, and in the distance, it's the flat terrace at the bottom. So this is where the cliff, the basaltic cliff goes. So again, the moraines form a nice sort of geomorphic marker in this relationship with the terraces. Next thing we do is mapping these terraces out. So one of the most important terraces, which is the one that forms immediately above the basalts, is shown here in red. So this is a regional terrace that is continuous throughout both river systems and shares this very large terrace patch here. So again, it forms a regional stratigraphic marker for the interpretation of the terrace stratigraphy. And just so you can see again a bit what this looks like, a quick zoom into this site here where we have probably the nicest set of terrace, continuous preservation of the terraces. This is what it looks like. You have these beautiful terraces that form after the deposition of these basalt flows, and then incise into the landscape and are associated with these terminal moraines. So we have a very clear association between the glacial geomorphology and the fluvial geomorphology, but we're looking only at the fluvial part. What do these terraces look like? So if we take their elevation and project them into this valley center line, this is broadly speaking what they look like. You see that so if we just highlight again this regional stratigraphic marker, so we're only really looking at the younger terraces, younger than this red one, so they're the ones that we might be able to date using cosmogenic nuclides. So these are the ones that form, this is the one that forms above the basalt flows. And again, just this very, very large regional terrace. So There are two very specific features about the terrace shapes that might be intriguing that I want you to keep in mind. And the first one is that the terraces, at least in the Shohen, so this is the northern river, they seem to show a decrease in slope immediately after the deposition of this red terrace, this T6. So as it erodes down, you have a change in slope, a bit like what you might predict by sort of a more climatically driven fluctuation. But broadly speaking, when you look at the more downstream portion of all these terraces, they're stacked parallel on top of each other. Ooh, no. They're stacked in parallel on top of each other, sort of following very much the slopes of the present day river. So this might be suggesting more of a base level lowering and that there is some sort of long-term overarching base level lowering or uplift signal that is affecting this. So this leads to the questions I want to answer. So when did these terraces form and how fast is this landscape incising? So for that, we did some cosmogenic beryllium-10 exposure dating of individual cobbles and sort of amalgamated pebbles and the depth profile. So mostly the samples looks like this. So either the top of very large boulders that got entrained at the top of terraces or whole cobbles. This is where we collected our depth profile. Unfortunately, you can't just dig into these terraces due to their composition. So we had to use where they have road cuts or dug gravel pits. And this is what the terrace generally looks like, which is pretty much like it looks like everywhere where we go in this region. So to start off, this is the depth profile we collected. We collected a singular depth profile for the youngest terrace in the Shohen. And using the HIDI 2011, I believe, 2010 depth profile model, we managed to extract an age of 33,000 years and an inheritance value that is 0.64 times 10 to the 5 atoms per gram. So we use this value to correct the inheritance, to correct the cosmogenic nuclide concentrations for all the other samples, for which these are the results. So, these are 66 data points widely distributed across the entire river network. But how do we make sense of these ages to actually interpret the age of these different terraces? So these are all of the ages. So these are stacks from the stratigraphically on top of each other. So the youngest terrace is at the bottom, oldest terrace is at the top. So this is just from the stratigraphic interpretation of the terrace levels, assuming that the ones higher up must be older than the ones below. If we just did a normal sort of probability density function fitting through the entire data set, we get this very high scatter ages. But actually, if we then select data clusters, so we remove the outliers, we start getting a much nicer pattern. Although for some of the samples, we actually couldn't really define a very specific function because there is not enough data. However, the ages are at least stratigraphically well constrained because of where they sit in the sequence. So in general, these are, this is the Terrace sequence, and these are the ages. So we have the youngest age sitting at 33,000 years, and the oldest age at about 1.5 million years. A very fast formation or turnover of terrace formation, starting at around 1 million years, and quite a significant gap in age between this sort of older set of terraces and this younger set of terraces. So perhaps an easier way to think about this might be looking at the terrace ages with respect to their elevation above the present day river. So here I've just plotted the terrace ages, so the interpreted terrace ages, as a function of the elevation of the riverbed for the Yoshohen to the north. So this is the one on top. and for the Rio Santa Cruz. So there are a few things that we can do here. So at least for the Rio Santa Cruz, we also have the basalts as an age constraint for all the ages of all these terraces. So one of the things that we can do is we can derive a sort of long-term uplift rate, or no, sorry, uplift rate, incision rate from the terraces. So we have rates that range between 100 and around 130 to 190 meters per million year. And but what you can see is that this rate is obviously not constant through time. So this rate is just derived by taking the elevation of the oldest terrace, so the oldest, best constrained terrace, this red terrace here, and dividing it by its elevation. But when we look at the incision rates that are derived from fitting linear regressions through groups of these data, you see that there is quite significant variation. We have this phase of very, very fast incision at starting around 1 million years, carrying on until around 800,000 years. Then a period of quiescence, a 400,000 year period of quiescence, and then rates return back to what sort of this more long-term erosion rate is. So just in summary, so all of these observations is that the terraces from the Rio Santa Cruz and the Rio Shohen, they form parallel to the present day river profile, stacked atop each other. The terrace ages range from about 1.5 million years to 33,000 years. In the Rio Shohen, so the river system to the north, you have the slopes decreasing, so they decrease by a factor of 2 between 1 million years and 900,000 years, but you don't observe this in the Rio Santa Cruz. Although when you look at the downstream portion, the slopes remain the same. And that you have a very long time scale. So on the time scale of 1 million years, you have an incision rate of around 115 meters per million years. But when you look at in more detail, you have actually a 3-stage transient incision history where the landscape is incising very fast, then slow, and then fast again. So how do the terrace ages compare to the climate record? So, how does this fit into a broader context? And can we actually observe the mid-Pleistocene transition in this record? So again, one of the really key things about this landscape is that we see these very nice associations of the moraine and the terraces, which means that we can really quite nicely associate the abandonment of the terraces to the retreat of the glacier, so the onset of the interglacial. So again, with the idea that the terraces are filling and aggrading when you have an ice advance and you have this increased delivery of coarse sediment right to the mouth of the river, you can actually grade the landscape. And that once the ice retreats during an interglacial, you have a decrease in the coarse sediment output, but you might have an increase in the discharge, which might cause the incision. So again, if we look back to this sort of key location, we have with this red terrace, so it's actually a really important location where we have, again, this sort of moraine and this 1.028 million year terrace. What is really special about this location is that this is the easternmost ice extent in Patagonia, and which is part of a glaciation which is known as the Great Patagonian Glaciation, which is the maximum ice extent in South America. And there's been lots of different studies that have dated this glaciation to starting anytime between 1.2 and 1 million years ago. But there's lots of evidence in the geological records that this has been more than a singular glaciation, but rather multiple cycles of glaciation that have incised into the landscape. So again, if we just put go back to our glacial records and put the ages of the terraces superimposed on our glacial records, what we find is that there's actually some pretty good agreement with the um, ages of terrace abandonment with the end of glaciations and the onset of glaciations. So, for example, we see this 100,000 year periodicity coming up, especially in the younger terraces, where they are associated with MIS 10, 8, 6, and 4, or at least this is how we have interpreted them. We also see that for some of the older glaciations, where they're associated with the end of the glaciations from MIS 20 and MIS 22. So this is already at the onset of the mid-Pliocene transition. However, we do see this sort of very, very short periodicity, lots of very intense glaciations around the starting at around 1 million years, which are associated with evidence for this Great Patagonian glaciation. So one of the things that is also interesting to note is that the terrace records in these rivers, so the ages of these terraces is generally consistent with the record of glaciations in southern Patagonia, where there is an apparent gap in the record between around 700,000 and 400,000 years, where there doesn't appear to be much of a record of glaciation in southern Patagonia, but it's actually very present in northern Patagonia. So this is just something to keep in mind for now. One of the things that we're trying to do as well is looking forward, at least is to explore a bit more mathematically how this climate modulation of aggradation and incision might relate to terrace formation. So Andreas Ruby and Fergus McNabb, who are working here at GFZ with me and my group with Taylor, are using some landscape evolution models of the GRLP river, models of alluvial rivers to model the behavior of this river and the formation of terraces. So stay tuned for work coming from them. So we see that the terraces seem to be forming in response to glaciations and show this 100,000-year cyclicity. But to be able to actually preserve these terraces and not get them overprinted with every single subsequent glaciation, you need to have a net base level fall. So in this case, we do know that the sea level hasn't really dramatically, even though there are very large fluctuations, there hasn't been a net sea level fall over the last 1 million years. So one of the things is that we're probably looking at some form of regional uplift. So what is actually driving this regional uplift? So again, we do have this evidence that the river these rivers have been experiencing an overall net uplift by looking at the shapes of these river profiles, so as in the stacks of the terraces. And that from these rivers, we do have this very long-term uplift rate of between 127 and 184 since 1 million years ago, which is broadly in agreement with other estimates of incision from the region. So again, if we come back to the basalts, there's good agreement, this long-term incision rate of about 100 meters per million years. Of course, this is lower because the terrace is immediately above the basalt. So also, there's ample evidence from uplifted marine rock that is exposed. So these are ancient shorelines that are exposed along the entire coast of Patagonia. And these have been uplifted and dated. A lot of these, both the marine deposits, but also the shorelines have been dated back about to MIS 11, so about 400,000 years ago. And they show uplift rates that range between 100 and 200 meters per million years. So we actually have some very good agreement between these coastal uplift rates, as well as the long-term incision rates that we have from the rivers, as well as good agreement between these coastal uplift rates as with the incision rates derived from the terraces, the youngest terraces. So there seems to be agreement on the same time scale as well as on the long time scale. So one of the first things that I ask myself and also get asked is, could could GIA be causing this? Could this be a GIA signal? Actually, GIA predicts, at least when you look at a Pleistocene or even a Pliocene correction, you'd sort of expect it to be on the negative side, so that there's a negative GIA correction, and the magnitude is just way too small. What about a glacial viscoelastic or elastic flexural rebound from melting and decreasing the size of the ice sheet? Well, the magnitude is way too high. So these we actually observe in the GPS rates of about 40 millimeters per year. So the magnitude is way too high, but also the length scale is completely off. So much of the uplift is really focused on where the ice was. So over the present day Patagonian ice field, it doesn't actually extend all the way to the foreland. So this probably doesn't really, we can't really invoke this as a mechanism. So what else is going on? So we know that this is a very geodynamically active region. So perhaps mantle-driven uplift. So the slab window, where you have the Nazca slab and the Antarctic, and the Nazca plate and the Antarctic plate subducting at different speeds. It causes this the slab window to form by the subduction of the Chilean triple junction. We know that we have a very hot mantle underneath, and we have very thin lithosphere, and lots of convection probably happening under there. So this is a very strong candidate. If we look at predictions of dynamic topography, so for example, this is a dynamic topographic change since 5 million years predicted from mantle convection models. The rates are too small to explain the change, as well as there is some, depending on the exact model that you look at, you might even predict some subsidence over the area of interest. So that's in this little box here. This is where we're looking at. Again, could some sort of isostatic mantle component. So for example, if the mantle has been constantly heating over time, if with the very thin lithosphere, could that be possible? So again, there's lots of evidence of this very, very hot, very, very low viscosity of 10 to the 18 Pascal second asthenosphere beneath the slab window. So if we just take some of the estimates of the lithospheric thickness and assume that you have heating of really hot asthenosphere underneath this slab window, a very simple sort of back of the envelope isostatic calculation suggests that we could have as much as 1 kilometer of uplift if this heating were to happen over the last 10 million years, which is the timescale of the opening of the slab window, which would translate into about 100 meters per million years. So what I would suggest is that this very hot, very buoyant asthenosphere, as well as the overriding lithosphere, is the main driver of this large-scale uplift in the region. And then we get to the problem. Well, how do we explain this sort of transient accelerated incision? So we can explain the long-term trends, but what about the transient trends? So again, we sort of observe this variable incision rate where we have this very strong acceleration of the incision of the Patagonian landscape around 1 million years. This is not just in our study. So there's a study by Jonathan Tabal to the north, so they're about 46 degrees south, where they've also dated a few outwash terraces surfaces and observed this very similar pattern where you have long-term about 140 meters per million year, but then this transient acceleration of incision at around 1 million years. So this is a regional signal. So whatever is invoked to explain this regional signal of incision has to be applicable not just locally. So we can't really use things like a drainage reorganization to explain this unless drainage reorganization is really happening on a continental scale. There is evidence just immediately south of, or just off of our study area. So this recent work by Veleda Paiva-Muller from using both apatite helium and helium-43 in the Torres del Paine complex. So that's just south of our study area. And they suggest that you can actually observe this sort of rapid cooling and accelerated exhumation in at around 1 million years. So, which is also what we see in the fluvial record. And a lot of people have suggested, so this is not just for this location, but particularly these two studies have been located, is that actually you have the very, very large Patagonian glaciations that happen at the same time of the onset of the mid-Pleistocene transition, and that you have the retreat of these very, very large glaciers. And as the glaciers get smaller, you get this isostatically enhanced possible rebound that then adds to and like acts to enhance the incision of the region by both so as well as getting the delivery, the very, very large delivery of water discharge, you also might have this enhanced sort of landscape incision. However, this would be so telling this apart from whether this is actually a glaciation, so a glacially induced or a mid-Pleistocene induced increase in incision rate is not hard, difficult to do. But there is definitely a climatic, I sort of suggest that there is a very strong climatic signal associated with this onset of accelerated incision at around 1 million years. So, in summary, hopefully you've convinced that the terraces show this transition in periodicities between the very short periodicities to the 100,000 year periodicities at around 1 million years, which reflect the change in orbital forcing at the mid-Pleistocene transition. I also show that you have this long-term regional uplift that is at very typical geodynamic rates that is likely driven by thermal anomalies beneath a thinned lithosphere associated with the slab window, and that this transient accelerated incision phase starting at about 1 million years suggests that the landscape as a whole is responding to the mid-Pleistocene transition, but to perhaps even broadly, it's just to climate, so to ice in general. And that this is very much a sort of mantle-driven and climate-modulated landscape. So thank you, and I welcome any questions.
Thank you very much, Victoria. That was fantastic. It was great to hear what you've been up to. So thank you very much. The chat is open, everyone. So if you have any questions for Victoria, please post them now. Perhaps I can sort of get in a bit quick before people start asking their questions. So hopefully it's a sort of fairly straightforward one. I was just wondering what your terraces are actually made of. So are they glacially derived? Are they coming from, way upstream? Do you have any sense for kind of what that material, where it's from, its origins? Yeah, that was it really.
So in terms of composition, so hopefully I might be able to use this as just a general guide. So in terms of texturally derived, it's like a very, I think, straightforward sandy channels with interbedded cobble and pebble layers. But in terms of the composition, in terms of the sort of like if they're derived. So one of the things that we do see is that when we go to the present day shores of the Rio Santa Cruz, we see that it looks a lot like this little corner here. So lots of cobbles and lots of pebbles. So the river seems to be able to, at least at present, seems to be, whether it's eroding into something that's aggraded, or whether it's actually transporting this size cobbles, it's hard to tell. We do know that a lot of these terraces have pretty much a glacial origin in the sense that a lot of it could be glacially derived material, and that is just some evidence from um, being in the field and going on top of what was originally mapped as a terrace, but was actually just a sort of outwash from a glacier. And in terms of composition, you have a lot of granites, which I'm guessing the only place that it could have really come from is from the Patagonian batholith, and which is mostly in this region sitting under ice. So it must be mostly ice derived, if
Cool.
that helps.
Yeah, no, that's great. Thank you very much. Okay, so we have a couple of questions in the chat. So the first one, so for the benefit of the audience, I'm just going to read these out, but you can obviously read along if you want. So David asks, is there an explanation for why there is not an MIS 12 or 16 terraces or glacial moraines in this area? Obviously, there's some of these that exist globally, and you had mentioned that they feature further north.
Yeah, that's a very good question. It's also one that puzzles me a lot. Partly because when you go to this, maybe just leave the moraines up here. So partly it's because just when you go to this part of the world, you can drive along these moraines, this whole sequence of moraines, and you kind of go straight from the sort of MIS 10 to the Great Patagonian Glaciation. So this like largest ice extent here. There's nothing else here. So and this is also seems to be reflected in a lot of the terrace records. So we have this lack of terrace records. So I don't think it's because of a lack of glaciation. So as I mentioned, the glacial records. Let me just get up the compilation that is quite helpful here. Yeah, um so the when you go to 46 degrees south, for example, so a bit further north in northern Patagonia, you see that you have a very complete glacial record, that you do have these very, very large glaciations. They seem to be leaving a record. But in this particular region of southern Patagonia, there isn't one. And I don't think, or at least my feeling is not that it's a lack of glaciation, but it's rather a lack of preservation. So because you have this sort of quiescence, this sort of reduction in the incision rate. I didn't quite get too much into this in my talk, but my current working hypothesis is that rather you have a decrease in the uplift rate. So it just means that rather than allowing for the accumulation, not accumulation, so the geomorphic preservation of these landforms, you overprint them until you have a renewal of this or this re-acceleration of incision again of uplift, which allows for the preservation of these terraces.
Okay, great. And then we have another question that asks about the large age uncertainties on your terraces. So is this due to kind of long-term like activity, or is it more down to the methods that you're applying?
So when you mean large age uncertainties, I guess, so for example, um, I'm assuming you mean the sort of age uncertainties here, so kind of the um that are sort of a 10% uncertainty. And I think that is partly because the terraces are very old. I mean, at least, especially the ones up here, the terraces are all very, very old. So the older the terrace, kind of like the larger the age uncertainty. But even still, for a million-year-old terrace, this is quite a good sort of cluster of ages. The scatter is actually very small. It's only on the order of about 5% once you sort of remove these outliers. And in general, I think it's just a case of when you're dating a surface this old, a million years of being exposed to the weather, to snow, to guanacos that walk over and kick over the cobble that you've decided to sample about 100 years, and so there's a bit of noise in the data. And I think that is just a sort of a factor of, it's just the data itself. Data is inherently noisy, but I think a lot of people who work on terraces and dating terraces might agree that the data is actually quite nice and nicely clustered. And so as far as it goes, I would say the ages are pretty well constrained, although there is quite a large error.
Okay, great. And so then we have another question that asks about your interpretations of why the fluvial terraces record a period of slow incision between 800 and 200,000 years ago.
Yeah, so maybe this might help. So again, we have this period of accelerated incision, and then you have very, very slow incision. And so one of the things that I would really like to point out is that in between, so here, these terraces actually have a very small difference in elevation, and there are no terraces missing. So at least in terms of mapping, and the same here, there's very little elevation difference between these two different terrace levels. However, there's a very large age gap, and there are no missing terraces. So for example, in here, I show that these two data points are terraces that we have mapped but haven't dated, but stratigraphically they must sit, sort of constrained in here somewhere. However, between these two levels, there are no missing terraces. So if we were expecting a constant uplift rate, a background uplift rate that is constant, that hasn't really changed over time, what we would expect is that the elevation of the terraces would be proportional to the time gap. So, just like a linear regression, as you'd expect. However, we don't see that. And because we don't see missing terraces, we don't see any lack of this big elevation difference. The only way to explain it is that then we must have had a slowdown in the uplift rate. And exactly what causes this sort of decrease in the uplift rate, it's not very clear. And I don't have a solid answer myself. So I have a few working hypotheses. So one of them is actually two. So one of them is, okay, if we have a region, so the region here is actually under this very hot asthenosphere, hot lithosphere that is very geodynamically active. If we have the viscosities that are so low, on the order of 10 to the 18 Pascal seconds, usual rates of uplift related to mantle convection or small scale mantle convection is on the order of 100 is sort of on the order of timescales of about millions of years. So if we have a reduction of one order of magnitude of the viscosity, so that's for normal mantle, 10 to the 19 Pascal seconds. So something that's on the order of 10 to the 18 Pascal seconds, you might have slightly faster overturning or faster, more vigorous mantle convection, which might cause some dynamic uplift, so sort of dynamic variations superimposed on this very long-term uplift. My other hypothesis is, sort of a bit inspired by some of the work. This is by Gaia Stuckey-Tekwe, who's at MIT. So this is some of the work she did, looking at some sort of transient landscapes, buried landscapes, which all point to sort of these transient uplift and subsidence on the timescales that could be on the order of million years, sub-million year uplifts and subsidence. So perhaps, if we can observe this, of course, this is in a plume setting where temperature variations are quite high. But if perhaps something similar is happening within the slab window, so some sort of thermal anomalies related to convection within the slab window, we could perhaps get these kind of accelerations and of uplift and slow down. So not really, a bit of a subsidence, which could cause both the lack of preservation of terraces and glaciations, as well as the decrease in the incision rate. But all of this is extremely speculative right now. Nothing is, I wouldn't say I have concrete evidence for why. It's something I still think about a lot.
Okay, great. Thank you. So yeah, if anybody has any final questions, if they wanted to just post them in the chat, I've got one more perhaps, and then we'll see if anybody else wants to weigh in. Otherwise, we'll bring this seminar to a close. So it was more about the big picture side of it. You started off, the motivation of this work was that you were talking about how we have different records that sort of pick out these orbitally driven sort of climate cycles. And I just wonder if you could comment a little bit more on the fact that you're observing these in this area. And I know obviously in other areas as well, we're seeing that. Are there terraces that potentially might pick up the higher frequency forcing in your area, or not? Yeah.
Yeah, so perhaps if I just go here, this might help show. So one of the things that I haven't really talked about is that so it's very hard to tell whether these terraces are specifically picking out sort of higher frequency fluctuations or not. But one of the things that was sort of like, I guess, um, is if you just kind of look at the terrace profiles, right? Like a lot of these are actually present throughout the entire system, which is quite surprising, at least. So if you just think about some of the work that Steffi Tefelde did, that kind of talks about the length, if you think about just sort of a rule of thumb, the length scale of the system, compared to the time scale that you'd expect these signals to propagate downstream from a purely sort of a climatic signal propagating downstream, as well as some of the work from Fergus and the GRLP model and kind of prediction of signal propagation downstream. From kind of like a sort of sediment transport along or signal propagation throughout the entire length of the system I'm actually quite surprised that we see these 100,000-year cycles, because the length of this system is very large. So if you just take the rule of thumb, you'd expect that 100,000 years cyclicity you'd only really see in systems a bit shorter than this. But one of the things that I find really interesting is that as you mentioned, like the sort of shorter frequency, sort of this higher cyclicity, we actually see it most prominently in the Rio Shohen, so this more upstream part, where you have a lot of really sort of small cycles happening in the upstream portion, where you have this very strong decrease in the slopes, as well as we have this very unique feature, which we don't see in the Santa Cruz, we only really see in the Shohen, which is a few of the terraces aren't really continuous throughout the entire length of the system. You only see it in the most upstream portion. So this is sort of the light blue and the dark purple terraces. They are not, you can't really trace them all the way downstream. They kind of merge into the lower terrace. And these are really very much formed during the period where we're recording these higher frequency glacial events. So I think that this is probably the best signal that we have, or the evidence that we have of higher frequency climate signals only really being preserved in the more upstream portion of the river system, whilst these longer term 100,000-year cycles, we actually see them throughout the entire length of the system. There's also some other complications that I'm not really going to talk about to do with drainage integration and so possibilities for that also affecting these terraces. But I think that this is probably our best example of these shortened frequencies only being recorded in the upstream portion. I think that's sort of what the question
Yeah, no, that's great. Yeah, sorry, I don't think I was necessarily particularly clear in my head what I was asking either, so it doesn't matter. But yeah, no, thank you very much. Okay, great. Well, thank you very much, Victoria, for a really great talk. Thank you to everyone who's attended the talk as well. It's great that we have a really nice turnout today. Next week, we will have a break and then we will return in a couple of weeks. I forget who's speaking, but anyway, there is another talk in a couple of weeks. But thank you very much. Yeah.
Thank you.